We'll first look at the two true-false questions. The first one, every subset of a regular language is regular. I put that in for every test. And believe it or not, there's still people who say true, but of course it's false. Every language is a subset of a regular language. All right, exponential time equals exponential space. Actually, subset, that's known to be true, but whether they're equal is open. Now, there's a context-sensitive language which is p-space complete. Well, the CS membership problem is p-space complete, and you can get that off the internet, which means there's at least one context-sensitive language which is p-space complete. All right, every finite language is regular. That's pretty trivial. Language, this one, a to the I, b to the j, a to the j, b to the I is context-free. Well, here is a context-free grammar for it. You notice how I start on the outside and move in, as opposed to the last time we dealt with it where there were two separate independent pairs. They were nested pairs here. Now here, the question is it true that every polynomial time language is context-free? Well, this language is clearly polynomial time in the sense that you could write a very quick program that would decide this language. But yet it's not context-free, as we know. All right, now, the regular expression equivalence problem is p-space complete. Now, that implies that every p-space language reduces to it in polynomial time, so it gives us a true for number 8. The union of two undecidable languages is always undecidable. Now, that's false. In fact, the intersection that, wait, it says the union is always undecidable. Oh, I was thinking of intersection. So, could even be sigma star would be the correct answer. In other words, if you take two undecidable languages and then take the union, they could cover each other's gaps, and the union could be decidable. Or, let's see, the union of two undecidable languages is always undecidable. No, the union could be all strings, which is decidable. All right, now let's look at number 10. Union of two recursively enumerable languages is recursively enumerable. That one's true. I didn't bother to explain that. Here is one that's interesting. The union of two co-RE languages is always co-RE, and I said hint, think. Now, what you're supposed to think about is this. If you have two recursively enumerable languages, the intersection is recursively enumerable. Now, that seems to be clear. Let me see. Why would that be true? Because if you have a recursively enumerable language is accepted by some machine, which means that if you have a string here, and you have a machine that accepts L1 and a machine that accepts L2, then you put in your string here, and if it comes out 1, then you put the same string into here and see if that comes out. So if the string is in the union, no, I was thinking of intersection. Let's put it this way. We have the machine that accepts L2. We put the same string in to both of them, and we combine these to get the answer. So this would be an AND gate here. So if both of them come out in there, then it's in there. So that means the intersection of two languages is RE languages is RE. No, that's the union, I'm sorry. No, this would be an OR gate. This would be an OR gate. So I'm wrong about that, because we're doing union, not intersection. But the intersection, well, here, the intersection is also recursively enumerable because we could put an AND gate there. All right, now, the union of, see, NC is co-NC. Well, this picture represents that. NC is all the languages which can be decided by, and then you put in your phrase there. Since it's a question of deciding, you definitely have an answer within polylogarithmic time. You just cross the wires and you've decided the complement language. True becomes false and false goes to true. All right, now let's look at number 13 here. All the regular expressions, the set of all the regular expressions over a given alphabet is an algebraic language. And as a general rule, algebraic languages are context-free, but not regular. So if someone says, if I say the language of all regular expressions over an alphabet is regular, the answer is false. But if I say it's context-free, the answer is true. All right, let's look at 14. 14 says, what about rush hour? Can you always get the answer? So there are a lot of websites that give a whole bunch of rush hour questions, and then they frequently give the answer. They say do this, then do this, then do this. The question is, if there is an answer, can they always explain the answer in polynomial time? Which, if it can, if it takes longer, then no one would be able to follow it because it would take exponential time to explain it. But the answer is nobody knows. If NP equals P space, the answer is yes. But no one knows whether NP equals P space. So this is an open problem. All right, now, let's look at this question. Is the factoring problem in both co-NP and NP? Well, it's pretty simple, pretty trivial to prove it's co-NP, because if the string is not factorable, then, if there are two factors, then you can exhibit both of them. But how to prove that it's in the class NP is actually pretty tricky. And I haven't gone over that, and I don't plan to. All right, now in this question, we have number 16, which is all regular expressions. 16. Oh, if the partition problem is in P, then P equals NP. Well, that's true because if any NP complete problem is in P, then P equals NP. So the partition problem is known to be NP complete, so therefore the answer to this one is true. All right, now we don't know whether factoring is in the class NP. And so, let's see here, this is 17. If someone proves that the factoring problem is in P, does that prove that P equals NP? Well, no, this says factoring NP is open. Factoring NP complete is open. If we could prove that factoring is NP complete, the answer to this would be true. But since we can't, we have this picture here. We have P, NP, and NP complete here. No, NP and, sorry, co-P. No, that's not what I meant to say. Let's do this again. I'll do it down here. This is NP, and this is co-NP. Now, is the intersection equal to P? Well, we don't know. The intersection of NP and co-NP might be P, but nobody knows. But if it isn't, the factoring problem is right in there. It could be that the factoring problem is outside of P, but it's inside of NP and co-NP. So the answer to this question is false. Because if we could prove this problem is in P, what does that do? That just means it moves over into this thing here, this little circle, and we still don't know whether P equals NP. So the answer to that is false. Let's look at 18. That's on the next page. NC equals P space. Now you know that NP is not known to be P, and you know that P is not known to be NP. NP is not known to be P space, and P space, P time, and P space, and P space, well, but when you close the chain up and you ask, is the one on the left equal to the one on the far right, NC equals P space, for some reason, unknown, 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 combining it together gives you false. So that means that the question, the NC is definitely not equal to P space, and that's known. Now, you can find that on the internet if you look hard enough. All right, let's look at 19. Co-NP is a subset of P space. Well, P space and anything space, like exponential space, is equal to its own co. It's only in time that it doesn't work that way, not space. All right, now, let's look at problem number 2. I didn't write this on the board, but what do you say, how do you prove it? The word is certificate or witness. Either one of those words is correct. Now B, the practicality of RSA one-way encryption depends on the assumption that the factoring problem can't be solved in polynomial time. This is an assumption, and no one has proved it. If anyone proved it, then the whole RSA encryption system would collapse. So it hasn't happened yet as far as I know. If somebody in the NSA has done it and hasn't revealed it, I wouldn't know, so it's still an open problem. All right, now problem C, NC, next class, is the class of language which can be decided in polylogarithmic time using polynomially many processors. All right, now here, this involves the pumping lemma. We're supposed to find a minimum pumping length for this particular language L. This language you can see L is context-free. Here is a context-free grammar for it. I couldn't find a simpler grammar, but there you go. Now, what's the minimum pumping length? Almost all students gave the answer of either 3 or 5. Both of those are wrong. The minimum pumping length is 4, and we'll go through that. First of all, in this example here, we break this is what I gave you to find out, break this string up into u, v, x, y, and z. Here u is AA, v is b, y is x is cd, y is the empty string, and c equals ee. Notice that vxy in this case, vxy, the length here is 3. And so that might trick you into believing that the pumping length was 3. Some people said the pumping length is 3 for this example, but that doesn't mean anything because the pumping length has to be global for the entire language. So the fact that 3 works for this example doesn't prove that 3 works for all strings. All right, now when I pump v and y up, I only add one letter because y is empty. Or I could pump down, getting this string. They're both members of the language. On the other hand, let's take a different example. A, C, D, E, E. Now this is also in the language because M could be 0. Now in this case, I'm going to break it up this way, vxy, which is 4. And so for this example, xyz is 4, vxy is 4. You might say, well, why don't I pick v to be the empty string and y to be the empty string? Well, that would work for this one example. Actually, it would not, because once you pump up and down, you wouldn't change it. V and y cannot both be empty. So if I take this example and pump up or pump down, I still stay in the language. Now the question is 4 really necessary? Well, let's take one of length 4. This string is in L and has length 4. And in this case, U and Z are both empty, which is loud, but V and Y are A and E. I can pump up or pump down and stay in the language. Now on the other hand, you notice that for CD you cannot break it up as U, V, X, Y, and Z because the length of CD is only 2. And therefore it's not guaranteed that you can find pumpable substrings. Now from this one example here, we can see that P can't be less than 4. However, if we think about it for a while, we can say that any string in this language either has a B in it or it doesn't. If it doesn't have a B, then any string of length at least 4 can be broken up. If it does have a B, then any string of length at least 3 can be broken up that way.